Welcome to video 4.1 in our first Principles of Astrophotography series. In this video we discuss the wave nature of light.
Light can also behave as a stream of particles, as we discuss in the next video.
But in this one we talk about the wave nature. Because deep sky objects are so far away, the only information about them that we are likely to ever receive is supplied by visible light and other forms of electromagnetic radiation that they emit, unless you want to get in a spaceship and travel for a very, very, very long time to find out information about these places.
Elon won't take me on his spaceship.
That's rude.
To understand light is to understand the universe.
This video is based on section 4.1 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 45, electromagnetic radiation. Electromagnetic radiation is a wave of oscillating perpendicular electric and magnetic fields that travels through vacuum at the speed of light. This speed c, the frequency nu, and the wavelength lambda obey c equals nu times lambda.
So nu here is the symbol that's used for frequency. It's a Greek letter.
If it was new to you, it was also new to me.
Yes. And the frequency is measured in cycles per second, or sometimes known as hertz. Hertz is the name of the guy who first observed electromagnetic radiation, but all it means is cycles per second. How many cycles does this oscillation go through per second? Lambda, so lambda here, unfortunately, and I know Ren gave me a hard time about this, but lambda, he's used to think about it being wavelength.
Yeah.
But we also use it for latitude. You just run out of letters in a hurry, and that's life. So usually from the context you can figure out what it's talking about. But lambda, sorry, this should be an L, lambda.
Oh, I get it.
Yeah?
Okay.
Yeah. So it kind of looks like it. Lambda is the wavelength, normally measured in meters, but it can be measured in any of a number of different units. The speed of light is 3.00 times 10 to the 8th meters per second. It's about 186,000 miles per second. The Earth to Moon distance is about 240,000 miles. So in 1 second, light will travel almost from the Earth to the Moon. So light travels very fast. And electromagnetic radiation is a wave of oscillating perpendicular and electric and magnetic fields. So denoted here in this figure, E here, the blue E, stands for electric fields. And B stands for magnetic fields. And it's in red. And what they do is, and what is a field? You already know what a field is, a gravitational field. There's a gravitational field that is outside the Earth that pulls us toward the Earth. Same thing is true for a very similar idea. At every point in space, a field is defined. It has both a magnitude and a direction. It's called a vector field. So for gravity, at any point in space, the direction of the field is down, and the magnitude is 9.8 meters per second squared. Did you think I'm a joke?
Yeah, it's just a vector from Despicable Me committing crimes with both direction and magnitude.
Does he say that in Despicable Me?
Yeah.
Oh, oh, did you just now realize that that's what he was talking about? Oh, I'm gonna have to watch Despicable Me again. But so electric field is defined a direction and a magnitude at every point in space, and magnetic fields are also. Electric fields are created by electric charges. So when you take your shirt out of the dryer on a really dry day, your arms kind of stand out from it, or you rub a balloon in your hair, you scuff your feet on the carpet, that builds up static electric charge, which creates electric fields. Magnetic fields are created by magnetic current, by electric current. So anytime you have a current in a wire, either a straight wire or a coil of wire, that'll produce magnetic fields. So those fields work together in concert to create these electromagnetic waves. All of them travel at the speed of light through vacuum. We'll talk about that in just a second.
Does it matter the medium that's going through?
And that'll be really important in a later video. The speed of light is less going through glass, for example, or
Fiber optic?
Yeah, it'll be less than the speed of light.
Who knew?
So, and that creates something called dispersion, which is an important concept. And the whole idea about light traveling different speeds in different media is why light bends when it goes into the glass or goes into water. You know, if you put a pole in the water, you can see that it sort of looks like it bends.
It's changing speed. Oh, okay.
Yeah. So we'll talk about that in later videos, but this is the basic idea. So the wavelength, lambda, is defined as the peak-to-peak distance. And we talk more about this in our book. But I think it's pretty obvious. Or you can go valley to valley distance. That's the same distance. So the length of the wave has to go up, and then back down, come back up again, etc. The frequency, so c is the speed of propagation. So this whole thing is propagating toward the right in this particular case. But if you look at a particular point in space, then what happens is the electric field is going to be positive, then it's going to be 0, then it's going to be negative, then it's going to be 0, and then it's going to be positive again. So that electric field is oscillating back and forth in space, and the frequency of that oscillation is given by this nu. So at any point in space, if you look at the electric and magnetic fields, it'll be oscillating back and forth, and the frequency will be given by nu. Good?
The magnetic field is directly opposite, or no?
So the magnetic field is perpendicular to the electric field. Thank you for asking that question. So if the electric field, for example, is up in an electromagnetic
Is this
wave,
the right-hand rule?
Yeah,
Okay.
It is. Then the magnetic field is going to be toward me, away from you guys, but toward me. You can't really see my finger, but pointing toward me. And the electric crossed into the magnetic field gives the direction of propagation. But the important thing is that the electric fields in this wave are going to be oscillating up and down. The magnetic fields are going to be oscillating side to side in concert to create this wave that propagates. It's so cool. I love physics. Oh my goodness. That's what electromagnetic radiation is. There are many forms of electromagnetic radiation, and that's what we'd like to talk about here. The first, the vacuum principle.
Vacuum. This is easy. Empty space is devoid of matter and is called vacuum.
Yeah, that's all there is to it. And so light travels at speed c, which is 3 times 10 to the 8 meters per second in vacuum. But what kinds of electromagnetic radiation are there? One is visible light. And visible light goes from about 400 nanometers, where 1 nanometer is 10 to the minus 9 meters. So a millimeter is 1,000th of a meter, and that's a really tiny amount. And you see that on a centimeter ruler, but that's 10 to the minus 3 meters. and a nanometer is 10 to the minus 9. So it's 1/1,000,000th of a millimeter. So it's really, really small measure. So visible light goes from 400 nanometers up to about 700 nanometers. There's really no sharp boundary on the visible range, because you can, you can see wavelengths better in the green than you can in the blue and the red, but it just kind of falls off. So it's not a sharp boundary that defines your visible spectrum. The frequencies of the visible spectrum, if you want to start at the longest wavelengths, about 700 nanometers, are red, orange, yellow, green, blue. Some people put an indigo, just kind of halfway between blue and violet. And if you want an acronym, the way we do it in physics is Roy G. Biv. So some guy whose name is Roy G. Biv, he gives you red, orange, yellow, green, blue, indigo, violet. Happy day.
Good for him.
Yeah, he's a good guy. So that's only a very narrow range of electromagnetic waves. And if you go to the right of R, longer wavelengths than the red, then you get to what's known as infrared. And I just remember it that way, that infrared is close to the red side, and so it's long wavelengths. And then ultraviolet is on the other side of violet, so shorter wavelengths than violet. And then X-rays are even shorter wavelengths. Gamma rays are yet shorter wavelengths. And then as you go in the long wavelength direction, so this is increasing wavelength, you get infrared, you get visible, infrared, microwave, FM radio waves, AM, and very long radio waves. Our universe sends out energy in all of these wavelengths. We learn things about our universe by capturing information in all of these wavelengths. There's extremely violent events that occur in our universe that send out gamma rays. These are super highly energetic, and we'll talk more in the very next chapter, or in the very next video, about how the energy increases with the frequency, nu, of the wave. These gamma rays are extremely energetic, very, very dangerous, like X-rays are dangerous. But you can also look at the universe in radio waves. Of course, in our hobby, we're mostly interested in just the visible, but there's a lot more out there. I recently contacted an astrophotographer who's doing some radio astronomy, some amateur radio astronomy.
Right.
He's built himself a radio.
A telescope?
Yeah, it's like a meter, and it doesn't have very high resolution, but he's looking at the universe with radio wavelengths. It's pretty cool. Okay, we already talked about this, but why don't you go ahead and read
You
it?
stole my thunder, but
Yeah.
I'll do my job. The human eye can see wavelengths between about 400 nanometers, violet, and about 700 nanometers, red.
Red. So, and sometimes they'll say it's between 400 nanometers blue, but it's on the blue end and on the red end. And the thing to remember is that a red wavelengths are the longest wavelengths. That'll become important when we talk about Doppler shifts, red shifts and blue shifts. A red shift means that you're shifting the wavelength to longer wavelengths, and a blue shift means you're shifting the wavelength to shorter wavelengths. Average wavelength, and we'll use this a lot in one of the upcoming videos. The average visible wavelength we're going to find by taking the low end, the blue or violet end, 400 nanometers, plus the red end, and then divide by 2. If you do that math, you get 550 nanometers as the average. Yeah, it's just the average. And the reason why it's useful is that sometimes you don't need the specific wavelength, but you want to calculate what's happening for sort of the average visible range. And so it's nice to know what the average wavelength is. And then C equals F lambda. And you can do this for anything. You can put in, for example, our Utah Public Radio, I think, is 90.9 megahertz. I'm sorry, we usually use nu. They used F for the frequency, but usually we use nu. 90.9 megahertz, that's nu equals 90.9. Mega is 10 to the 6. And you can plug that in here and plug in the speed of light, which is 3 times 10 to the 8th meters per second, and you can calculate the wavelength. It's just that simple. You can do it for any wavelength you want. But for visible light, we can calculate the actual frequency associated with the average visible wavelength by taking C equals nu lambda. And then this bar over the lambda means that it is the average. So that's what that bar means. So if you see a lambda with a bar over it, it means it's the average wavelength. And then the frequency associated with that average wavelength, you can calculate by dividing both sides of this equation by the average wavelength, and you get that the frequency is C over lambda bar. That's this equation here. If you plug in 3 times 10 to the 8 and 550 nanometers, and you need to convert the nanometers to meters, I'll leave this as an exercise for the reader, if you're interested, to calculate the frequency associated with the average wavelength. So that's about 5 times 10 to the 14 hertz. So I don't know about you, but 10 to the 14 is a big number. I like to think about it in terms of millions or billions. A million is 10 to the 6. A billion is 10 to the 9. And a million times a billion would be 10 to the 6 plus 9. It'd be about 10 to the 15. So we're talking about roughly a million times a billion cycles per second is how fast light is oscillating back and forth. Thanks so much for watching.
Yeah, we'll see you next time.